Okay, everybody, this is the lesson that I'm going to try to connect calculus with business or economics. And so when you're talking about businesses, you really have two things that they worry about. Revenue, money coming in, and cost, money going out. So if you're looking at cost, and if I were to model it with a function, let's call it C of x, if that's the total cost of a company that's producing whatever thing, like X units of a product, we call this the cost function. And if the number of items produced is increased from some starting amount, X sub 1, to X sub 2, then the additional cost can be noted like this. It's really the cost function evaluated at the X sub 2 minus the cost function evaluated at X sub 1. Or sometimes they'll use this notation, change, the change in cost. So this triangle is like delta, which represents the change. So the change in the cost. Now the average rate of change of the costs, think about what you did in Math 10 with the slope formula, remember? Y2 minus Y1 over X2 minus X1. Well, the Y2 was like the change in the Y value of the cost divided by the X values change, so the change in the X. So in this case, if I were to replace delta C with our expression above, that's the cost function evaluated at X sub 2 minus the cost function evaluated at X sub 1. And then, of course, the change in X would be X sub 2 minus X sub 1. Okay? Now, sometimes we can make this lovely substitution. So I'm going to say note. Okay? Let me say that X sub 2 is the same thing as X sub 1 plus the change in X, delta X. If you don't know where I got that from, I just took the denominator here and I just rearranged it. And if I did it something like that, then that whole entire expression, this average rate of change expression, then would become C, instead of X sub 2, it would be X sub 1 plus delta X minus C of X sub 1 all over, well, it would be X sub 1 plus delta X minus X sub 1. And if you're thinking, where have I seen this before? You should be thinking about that. Yes, delta X. Perhaps this is kind of the expression for the derivative. But what am I missing? Yes, I'm missing some limit notation. So what is the instantaneous rate of change then? Remember that was the average rate of change. The instantaneous rate of change is just the limit as that delta X approaches to 0 of the change in C value divided by the change in the X, which just happens to be then the limit of delta X approach to 0 of our lovely expression that I just wrote from above. And I hope you recognize this as, yes, the definition of the derivative. So I'll say this is the derivative of C dC over dx. And in business, there's a special name given to this expression. It's called the marginal cost. Marginal. M-A-R-G-I-N-A-L. Cost. Those of you who talk AP economics, you're like, oh yes, I remember that. Now, since X in the business world can only take on the integer values, I don't think anyone sells like half a calculator, it may not make literal sense to let X or delta X approach to 0. But we can always replace the C of X function by a smooth approximating function. So in this case, the smallest it could be close to 0 is probably 1 item. So therefore, if we're taking delta X to be equal to 1 item, 1 additional item, and n, right, the number of items that you're producing is really large, like 100 million, then yes, 1 compared to 100 million is really, really small. That's pretty much like it being equal to 0. Okay? And so what we have here, therefore, is that the derivative, and I'll use this notation now, C prime of n, and that would represent the derivative or the marginal cost. That would be approximately equal to the cost function by plugging in n plus 1 items. So this is really the total cost of n plus 1 items minus C of n, which is really the total cost of n items. Okay? So therefore, the marginal cost of producing n units is really approximately equal to the cost of producing one more item, or the next unit. So let's look at this example now. So I have a function. It's a lovely cost function. It's a polynomial, thankfully. And I said find the marginal cost of this function, and then compare the marginal cost at the production level of 100 units with the cost of producing the 101st item. So let's find the marginal cost first. The marginal cost, once again, yes, it's just the derivative. Do you guys still remember how to do derivatives? The derivative of 420 is 0, thank you. The derivative of 1.5x is 1.5, and the derivative of 0.002 times x squared is just plus 0.004x. Nice. And if I asked you to find the marginal cost at the 100th unit that's being produced, you would just plug in 100, and then you would calculate, and I think that's 40 cents, or 1.4, so that's $1.90. So really what I'm saying is the marginal cost, okay, the change in the cost structure, if I've given one extra item, is approximately $1.90. Now, I said let's do it the other way. I'm actually looking at the cost function and looking at the actual cost of the 101st item. So the actual cost of the 101st item would be equal to the total cost of all 101 items minus the total cost of the 100 items. Right? Remember, C is a total cost function. So then what you need to do is just use your polynomial, plug in, whoops, what happened there? Plug in 101 minus 420 plus 1.5, plugging in 100 all squared, and then just calculating that for the answer. And I've just done it, and the answer is 1.902. Well, when rounded, that's pretty much $1.90, and look, they are the same thing. Now, on to the next page. Recall that the marginal cost function is really the rate of change of the total cost with respect to x, also known as the derivative, right, of the cost function, and we denote it by this notation, c prime of x. And most of the times, this is a typical graph of a cost function, okay? LTC just means long-term costs. And I'm going to ask you to think about this idea, concavity. By looking at this graph, how could you describe the cost function using the ideas of concavity? This looks like it's concave. That's right. Down. And then what happens afterwards? Concaving up. So, for those of you doing economics, how would you describe this phenomenon? Well, I'll say it's initially the total cost curve concaves down. How come? Because of economies of scale. I hope you've seen that term before, for those of you who've done economics. For those of you who don't, the idea is at the beginning it might cost more to produce it because you're doing it new, but as you produce more and more and more, you get used to it. The fixed costs that are required at the beginning to produce something can now be distributed over multiple items, and that's why the curve flattens out, because the total cost gets less and less as you produce more and more items. That's why when you go to a superstore and you buy bulk, it's usually cheaper than buying one item, right? So the idea is you have a more efficient use of fixed costs. But eventually what happens too? Well, eventually it actually concaves up though. But I'll say eventually it concaves up. And what does that mean then? Or why? Well, because sometimes you grow too big. and then you produced too many items. And when you produce too many items, perhaps you need to store these items, and you can't find a place to store them, or storing also takes, there's a price to pay for that. So therefore, the idea here about growing too big is you really have things that are due to maybe perhaps overtime costs, producing too much, okay, or what I'll call inefficiencies. Okay, so there is a sweet spot, right? And that sweet spot, of course, is the inflection point. All right. Well, how would we go about finding the average cost again? So once again, the average cost, the average of anything is really the total cost divided by the quantity. And remember, our expression for total cost was C of x, and our quantity was x. So we have something like this. Well, my question to you here now is, well, a company really wants to do what? Does it want to maximize costs? No, it wants to minimize the average cost. So my question now is, how can we figure out where the average or the minimum of average cost will be? How do we find minimums using calculus? Yes, if you thought about this and said, well, we need to take the derivative. Yes. And then set the derivative equals 0. Yes. And then solve for s, or solve for x. Yes. So let's figure out the derivative of average cost. I'm going to use AC to represent average cost. So now AC prime is the derivative of average cost. And since this is my function here, I see I see division. That's right. The quotient rule I need to know. Here we go. Low D high, which is C prime of x, less high D low, which is just 1. Draw a line, and then below put the square of the low. There we go, x squared. The idea now is to then set the derivative equal to 0. And if that's the case, then we really don't care about the denominator, right? We just really worry about the numerator being equal to 0. And then remember, the idea was to solve for x. Okay, so I see there's x by itself like there, so let me move the negative cx to the left side, and then I can now divide. There's x, right? Interesting. Now, what does this actually show, though? Maybe this is kind of weird because you're like, well, what does x mean? That's the total cost divided by the derivative. That's where the minimum is. Yes. Okay. Or another way of thinking about this is if I were to rearrange this, I could have had C prime of x being equal to C of x divided by x, right? That's me taking this line here and isolating for C prime. Now this is interesting because what is this lovely expression again? C of x over x? That's the average cost. Right. This is the expression for average cost. And those of you taking economics, you're like, oh my, what did Mr. Lee just prove in terms of calculus? That now this is average cost, and this over here represents the marginal cost, the derivative, remember? Marginal cost. So really, to minimize average cost, what do you need? You want the marginal cost to be equal to the average cost. And you should have learned that in economics as well. And here's the calculus proof. So, looking at example number 2 now, I've got another cost function. Can you actually find the average cost, the marginal cost, and then find the production level that will minimize the average cost? So once again, average cost equals to total cost divided by the quantity. In this case, we have 2 root x plus x squared over 8,000 all over x. And I can simplify that. That's just 2 over root x. And then x squared over x is just x, so x over 8,000. Then I can quickly figure out the actual average cost at 1,000 units by plugging in 1,000. I wish the number was 100, but oh well, it is what it is. And I'll do the calculation. I got about 19 cents per unit. Okay, so that's the average cost. Marginal costs. Marginal cost, of course, is just a derivative of total cost. Lovely derivatives. This is what? 2x to the power 1/2. Take the exponent down, reduce it by 1, x to the negative 1/2. Same thing here, take the exponent down. That, I think, simplifies to 1 over root x plus x over 4,000. Woohoo! And then if I want to actually find c prime of 1,000, then, of course, I'm going to plug in 1,000. It's just 1,000. And I will find that this actually equals 28 cents per unit. Okay? Now, it's asking, find the production level, meaning how many values of x, right? I want to find the production level that will minimize average cost. And from above, we know that to minimize average cost, you want to make the marginal cost being equal to the average cost. So here's our marginal cost, c prime of x, equal to marginal equal to average, which is just c of x over x. So ultimately, it's this expression, 1 over x plus x over 4,000, that being equal to the other expression, 2 over root x plus x over 8,000. All right? And I'm going to ask you to solve it. So go ahead and solve it yourself. Boop, 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 boop. I'm too lazy. Okay, fine, I'll just give you the answer. X actually equals to 400 units. Nice. Okay? And now, remember, you should also double check to make sure that this is the minimum, right? Just by letting it equal to 0 and solving does not guarantee that this produces a minimum value. So in order to do that, one of the ways to figure out if it's a minimum is to take the second derivative. Check to see if minimum by finding the second derivative. So c double prime of x, you gotta figure that out. And then after you've done that, I'd like you to plug it in and evaluate. And I'm going to tell you that this is definitely bigger than 0, so therefore this concaves up. And yes, we did prove it is a minimum. Woo! So, I've only touched on one side of the business kind of equation. Costs. I can also talk about the other side, the more fun side for your business. Yeah, it's the revenue and the profit that comes in. So let's think about this. Revenue and profit. Revenue is just money coming in. Cha-ching, coming in. Yes, but it doesn't mean that that's how much you make, right? Because the profit is really what you make, which represents the idea of the money that comes in minus the money that goes out of your business. So let's consider marketing. And this P of X, this is small p, okay? P of X. This is the price per unit that the company can charge if it sells X number of units. Here we have something called capital P, and capital P I'm going to denote as the demand function, okay? Or some people say the price function. And we will expect it to be a decreasing function because usually what happens is if you produce more, right? More out there, you charge less. If you're scarce, you're the only person, you're the monopoly, then you can charge more. So if X units are sold and the price per unit is this little p of X, then the total revenue is defined as taking the price multiplied by the quantity that you sell. So the revenue function, okay, in this case, I'm going to write it in here, let's call it R of X. That would be equal to me taking the price, which is P of X, multiplied by quantity, and the quantity right now is X. Or sometimes math people prefer to have the X in front, X times the function P of X. That's how we figure out revenue. Now the derivative R prime of the revenue function, can you guess what that's called? The marginal revenue. And that really is the rate of change of revenue with respect to the number of items sold. So, why do we care? Well, we care because we care about profit. Total profit, of course, is revenue minus the cost. And if I have this profit function, which I'll call capital P of X now, okay, this is capital P, that will be equal to capital R of X, the total revenue, minus the total cost. And then, of course, if I have capital P prime, then we will represent this as the marginal profit. And that, of course, is the rate of change of profit with respect to the number of units sold. So let's use some calculus now and apply it. So I've got a friend, it's Terry. He doesn't do much in the summertime, but he does sell necklaces on the beach. Last summer, he sold necklaces for $10 each, and his sales on average were $20 per day. Not bad. But when he increased the price by $1, he found that he lost 2 sales per day. Don't be greedy. So I want us to do these 3 parts. Okay, and the first part says find the demand function. So the demand function is really what is the relationship between price and quantity, assuming it is linear. Okay, and then after that, find the revenue. So if I'm assuming something is linear, then you're thinking y equals mx plus b. Y would be your price. X would represent your sales, or the number of units sold, right? Your quantity. So how do we figure this out? Well, M, of course, stands for the slope. The slope would be the rate of change of price with respect to quantity. When the price increased by $1, he found he lost 2 sales. That's pretty sad. So that's negative 1/2. And then we're going to multiply that by X, and then plus B. We do have some initial value here, $10, 20 days, or 20 per day, I should say. So 10 equals to negative 1/2 times 20 plus B. So I think B equals to actually 20, right? Half times 20 is 10. Move to the other side, 10, 10, 20. Good. So therefore, my price function is equal to negative 1/2 X plus 20. Well, what's my revenue function then? Revenue, then of course equals to price times quantity. And so the price here is negative 1/2 X plus 20, and my quantity is X. So if I were to multiply this out, you'll get, a quadratic. And I don't know if you remember doing these questions from pre-Calc 11, but we did stuff like that there too. Okay? How should you price it so that you maximize revenue? You want to maximize revenue, you want to find the derivative of revenue. Set it equal to 0 and solve. Woohoo! Oh wait, that's not the price, right? By the way, I should also check that this is actually a minimum. I'll use the first derivative test now. This time. Let's see, the function is negative, then positive. Yeah, that's the minimum. Good. But I'm asking for price, so now go ahead. Now go ahead and plug into price, or plug it into the equation, the demand function. So P of 20 now equals to negative 1/2 times 20 plus 20. That's negative 10 plus 20, that's 10. Woohoo! So therefore the price should be $10. Now, what about the next part? What happens if now we figured out that the material for each necklace cost Terry $6? What should his selling price be in order to maximize profit? Now remember, the idea of profit, once again, is revenue minus cost. So revenue's function is that lovely parabola. The cost function in this case is $6, so it's really 6 times x. It's linear. And then now if I want to find out what I should be maximizing for profit, I want its derivative. And I want to set that equal to 0. and I find that I shouldn't be selling it at, I shouldn't be trying to sell 20 of them. I should only sell 14 of them. And the price, once again, that I should be charging to maximize profit, right, which is really how much money I really make, not revenue, would be, I should be charging them at a price of $13. And that's how calculus and business go hand in hand. Okay? Now I'm going to go on and talk about one more concept. This one you might have seen before. It's called the price elasticity of demand. Oh, those of you taking economics, you're like, oh yeah, I remember these ugly terms. Oh no. So let me talk about this, and then I'll do 2 examples, and I think I'll call it quits for this lovely video. It is a longer one. I apologize. But the price elasticity of demand, by the way, also known as demand elasticity, is defined as the percentage change in the quantity demand divided by the percentage change in the price. So this is quite often used to gauge what kind of pricing structures and models we should do. It's not always just about finding the maximum, right, or the minimum. It's about how to get there as well. So look at what I said, the percentage change in quantity demanded. That's like me saying an infinitesimal change. So I'm going to use this notation dq divided by q divided by the percentage change in p. That's like dp over p. And if I were to rewrite this, that's dq over q divided by dp over p. Dividing by a fraction, same thing as multiplying by this reciprocal. And then if I were to separate these and put them together, that would be p over q times, and if I put these together, that would be dq over dp, which this is some sort of derivative, right? This is the derivative of, this is the derivative of quantity with respect to price. So the law of demand implies that this derivative, the rate of change of quantity over price, should be less than 0. Okay? Meaning, think about it. If I were to have more items, then the price should go down. So these are opposite directions, right? If the quantity goes up, the price should go down. So one's positive, one's negative. So therefore, the expression here should be negative. Okay? So once again, why do we care about this? Well, consider this question. How will revenue change as we change the price? So let's do this by taking a look at, once again, what revenue is. Revenue equals to price times quantity. Now note, this time I want it to be as a function of price. So I'm going to keep price as p, and I'm going to define quantity as the function q of p. Okay, so once again, note, this time quantity is a function of price. In the previous example, I think we did quantity as a function of the number of units sold. Okay. And in this particular example, if I'm trying to find now the derivative for revenue in terms of P, notice I have 2 things multiplied together. Product rule. A prime B plus B prime A. Haha, see all this beautiful review. So the derivative of A, the derivative of P is just 1, times B, which is just Q of P, plus B prime. So that's the derivative of Q of P times A, which is P. And notice if I have this lovely expression, notice that both of the terms have actually, they don't have anything, but I'm going to actually try to factor out Q of P. Factor out Q of P, and you're like, why? I hope you'll see why in a second. I get 1 here, and then now I also have here, plus, what's wrong with my colors? Plus Q prime of P times P divided by Q of P. And you're like, what's the big deal here, Mr. Lee? This looks messier than the previous line. Perhaps, but I want you to focus on this. What is that? Sorry, I should have said, what is that? Maybe that's better. Q prime of P, that sounds like the derivative, doesn't it? dq dp. And then we have P, and then we have this Q of P, well, that's just Q. Where have we seen that before? This expression just represents price elasticity. So note that the quantity, which in terms of price, Q of P is always positive. So the sign of R of P is completely determined by the quantity in the above brackets here, right? So what determines if this is positive or negative is really that expression that I highlighted in yellow. Q prime of P times P divided by Q of P, which is precisely the demand elasticity that we defined just above. So what I mean by this is then, thus in size, in absolute values of elasticity relative to 1, that will determine how the revenue changes as price changes. So I'll talk about more of this in a sec, but suppose you're a manager of some store and you want to find out how customers will react when you introduce the price of a good. So a good decision would be the following. If the increase in price increases revenue, let's think about that. I charge more, I get more. Think of like those luxury, handbags, that kind of stuff. Okay, that would probably be a good decision, right? A bad decision would be if I increase the price and it decreases the revenue. Okay. And so how do we figure out that balance? Well, we use elasticities really to find out how sensitive consumers are to price change. So turning the page, in economics, we have this particular idea. When the elasticity, when this E value, is greater than 1, we say the good, or that item that you're trying to sell, is price elastic. And therefore, management should decrease the price in order to have a higher revenue because, well, in this case, the percentage change in quantity is much bigger than the percentage change in price. When this value is less than 1, the economic term is called inelastic, and management then should increase the price to have higher revenue because in this case the percentage change in quantity is actually less than the percentage change in price. And then when E equals to 1, we call this good price is unit elastic. And this is really the optimal price, which means it maximizes revenue. Why? Because the percentage change in quantity actually equals the percentage change in price. Those of you in economics, I hope you're seeing this connection now. I hope it's beautiful because you're like, oh, I see where calculus comes into play. So, according to economic theory, the primary determinant of this price elasticity demand is really the availability of substitutes. So the idea is you can sell something for more and people will buy it if you're the only person on the market. But once a substitute comes in, like a knockoff from China, then you've got problems because then guess what? You have competition. So when many substitutes are available, then the price demand is usually elastic. For example, if the price of Pepsi increases, consumers can easily switch to Coke. So the price elasticity of Pepsi is really, really high. Whereas if you have an item that there are very few substitutes, the demand is quite inelastic. Even the price of a basic food item, as it increases, one has to buy this food item to survive. Perhaps it'd be like, I don't know, something. So, for example, in much of the world, rice is a staple food item. And it is an item which is highly price inelastic because guess what? Everyone eats rice, and everyone needs rice. Okay? So let me try to show you an application of this. I think I got 2 more examples. I know this is really long, so I'm just going to do one, and then maybe I'll leave the last one for you to try. But suppose the demand of the functions for OPADs, yes, no iPads, can't do those, we have OPADs, is given by this function q equals to 500 minus 10p. So I want you to compute the price elasticity first. So the price elasticity is this function e, and that's equal to this thing dp dq times p over q. Okay? Now, dp dq means I need to find the derivative of my quantity function with respect to price. Did I write this wrong? I'm so sorry. I forgot. These are always opposite. If p is in the top, then it's dq. My apologies. dq over dp. That's easier. So in this case, the derivative is negative 10. So really what I have here is that this dq dp, that's negative 10. P is just p, and quantity in terms of p is now 500 minus 10p. So I get this expression, negative 10p over, what is it? (500 minus 10p), right? I can simplify this by taking out a 10 factor from the bottom, and I get negative p over 50 minus p. Okay? Or, if you don't like it, you can take out the negative and stick it in the bottom, p over p minus 50. Either or is fine. This is the formula for price elasticity. Now, so what? So what's the price elasticity of demand when the price here is equal to 30? So now just plug in 30, right? So plug in price equals to 30. E equals to, here we go, 30 minus 50. Then we get equals what? 30 over negative 20. That equals to negative 1.5. Now remember, I think I made a comment earlier that we really want the absolute value. We don't really care about the negative because we know it's always going to be negative. So I really should have said this. Oops, I did. I forgot. Don't forget, it's the absolute value. Absolute value. So I should absolute value, absolute value, absolute value. So the answer here is 1.5. So this number is 1.5. By the chart above, that means it's bigger than 1, so this is price elastic. Since the absolute value E is bigger than 1, this is price elastic. So therefore, what should we do? To increase revenue, you need to what? Decrease price. So there must be a lot of substitutes for this OPAD out there. Yeah, like the iPad. So now if I ask you what is the percentage change in demand if the price is 30 and it increases by 4.5, well, here you can use the same idea of elasticity, and I'm going to go back to our original definition, dq over q divided by dp over p, which of course then leads us to doing something like this, because if I were to solve for dq over q, which is what I'm asking for here, dq over q just equals to E times dp over p. Then what I'm saying now is just plug in these numbers. So E is what we found earlier, negative 1.5. This dp over p represents this increase of 4.5%. So let's write that as a percentage. And then you will see that if you calculate this, you'll get this lovely number. And that means that the demand will change. In this case, that was an increase, so the demand will be a decrease by 6.75%. So at this price point, if you increase the price by 4.5%, expect your demand to be reduced by 6.75. Okay? All right. I think I'm done talking. I know this is a really long video. I'm so sorry. But I've got 2 more examples here, and I'm going to ask you to try them yourself and then come back and check the answers. I will write the answers here. Okay? Press pause. You try, then come back. Max revenue, remember? Max revenue, that means elasticity equals to 1. Approximately $8.16. Is that what you got? You got it right. Hockey. When will hockey come back? Problem here. I need quantity as a function of p. It's time to do some algebra. Square root of p equals to 100 minus q over 10. 10p, 1,000 minus q. Q would be now 1,000 minus 10 root p. P, Q. Ooh, derivative. Good question. What's the derivative? What's dq over dp? Negative 5. P to negative 1/2. Negative 5 over root p. Negative 5 over root p. Okay. Since I combined this and this together, the current ticket price is 100. Yikes! Running out of batteries. 100. So if I plug that in here, 10 squared. Is that 10? Current price is P. Yeah, P. Don't plug it in there. What am I doing? Plug it into here, perhaps. Oh, what am I doing? I don't need that. Current price is 100. Just plug in 100. Duh. So just plug in 100. Don't need to do anything. What's that? Negative 50. I think that's 900. Don't forget absolute value, all this stuff. I got 1 over 18. Running out of battery, so I'm trying to finish this. This means that it is price inelastic because it's less than 1. So therefore, what should you do? You really should increase the ticket price, right? You're the only game in town. There's no really substitute for you. And you should increase the ticket price until it eventually what? You get elasticity equals to 1.